So I'm going to go through the examples that I skipped today in class. For this first one, we are looking for intervals of increasing and decreasing. So we're going to go through this same process again. We start by finding critical points. So f prime is 3x squared minus 6x minus 9. And then we set this equal to 0. So to solve, we can divide the whole thing by 3. Okay, and then factor. So x is 3 and negative 1. So we have these two critical points here, okay? And then we need to do test points on a number line. Now, I didn't really talk about this part earlier in class, so and this is really, I mean, it's not necessary information, but it's something that can make your life a little bit easier. When you are checking the sign of the derivative, okay, plug your values. If you even use values, really, I'll show you that we don't actually need to completely plug numbers in, but check your values with the factored form of your derivative. Okay, the reason is because it's a lot easier to plug something in here and then just subtract a number and add and then multiply to find the sign, as opposed to plugging it in back here and having to do this entire computation, or even back here, okay? Because remember that we only care about what the sign of the derivative is, not how big or how small it is. So what I mean by that is I can not do any numbers at all and still get a sign chart, because I can say, label this as f prime. So I can say if x is less than negative 1, something to the left of negative 1, this factor is going to be negative. This factor will also be negative, and the product of two negatives is positive. Okay, so if you see, I didn't actually say, okay, well, let's try x equals negative 2. I just know that something to the left of negative 1 will make both of those factors negative, and then the product is positive. And then I also know that since this factor is raised, it's a single factor, like it's not squared or anything like that, but because x plus 1 is a factor, when I switch from the left side of negative 1 to the right side of negative 1, this factor will change signs. So then I'll have a negative times a positive for anything in between here, meaning my product is negative. Okay, and again, I didn't even really need to plug in a number to figure that out. And then as I move from the left side of 3 to the right side of 3, this right here, this factor will change signs. So then that's going to be positive, and that one stays positive. So my product is positive. Okay, so then what I end up with is a derivative that is positive on these two intervals and negative in between. So I can say that f is increasing on negative infinity to negative 1 and on 3 to infinity, okay? And then f is decreasing on negative 1 to 3. All right, now a couple finer points about notation and stuff. I mentioned this in class, but I do not care if you use a comma or a union sign or the word and. It does not matter. I'm not going to be particular about that. The AP test won't be particular about that, because it's not really about how you write your set notation. It's just identifying the intervals, okay? And then also, I did mention this, but I want to reiterate, we can use open or closed parentheses or brackets for intervals of increasing and decreasing almost all the time, okay? In the case like this where we have a continuous function with no holes or asymptotes or anything like that, it would not matter at all if I were to write this like this. Infinity is always open, but this would be exactly the same answer. Both would be completely acceptable. You might see one or the other on a multiple choice test, okay? Or like, you know, a solution somewhere, okay? However, if there is an asymptote or a hole or something like that, the brackets would be incorrect. Okay, so think about like y equals 1 over x. Here I would say, I can't say that the function is decreasing from negative infinity to 0 and 0 to infinity and then combine that and just say it's decreasing from negative to positive infinity, because it's not actually decreasing at 0 because it doesn't exist. Okay, so there are certain instances where a closed interval does not work, but there's never an instance where an open interval doesn't work. So to be on the safe side, always go with open intervals. Okay, again, you might see closed intervals somewhere. So if you're checking your answers or looking at a solution or a video and they use closed, it's not a big deal, okay? But I recommend that you always use open. The other thing is that intervals of concavity always have to be done as open intervals. Okay, all right, and so this one right here, let's repeat the process. Find y prime. Y prime is 3 secant squared x, and again, we set this equal to 0, and then we can divide by 3 on both sides. Okay, so secant squared equals 0. If you remember, secant squared's graph looks like this. Okay, this is just a rough sketch here, but secant squared's graph looks like this, and the lowest point on these curves is 1, and then the highest point on these curves is -1, so the axis is in between here. So this is actually never going to be equal to 0, all right? So there is no solution to secant squared x equals 0. And this is just the graph of secant, but even if I consider the two factors separately, like secant times secant, it still never hits 0, okay? However, that doesn't mean that there are no critical points, because remember that we also need to consider where f prime does not exist. There are places where secant doesn't exist. If you don't know what the graph of secant looks like, another way to think about this is write that as 1 over cosine squared. Okay? Now, does it ever equal 0? No, it does not, but there are places where cosine is equal to 0, and if cosine is equal to 0, we have division by 0, meaning that this is not going to exist. We're going to have a problem here. So we can figure out where cosine equals 0, and that's going to be a critical point. All right, so cosine equals 0 at x equals pi over 2, 3 pi over 2, negative pi over 2, 5 pi over 2. Okay, so we definitely can't list an infinite number of points. So what we can do is we can write in set notation. We can write the set of, oh, actually, hold on. We don't care. Because we're not trying to write all these out. We just need to know where the function's increasing, decreasing. Okay, so in words, I'm going to write this and say that this is our critical points are going to be pi over 2 plus multiples of pi. So pi over 2 plus 1 pi plus 2 pi plus 3 pi or negative pi. That's gonna be enough for me to know where all of my critical points are. Okay. So on a number line, I'm just gonna put a couple of them to check. So let's do negative pi over 2. Positive pi over 2. To the left of negative pi over 2, now I'm checking secant squared or 1 over cosine squared. Go back to the derivative. 3 doesn't matter. So to the left of negative pi over 2, well, anything squared is going to be positive, so that's positive. In between these, again, something squared is positive. To the right, so again, something squared is positive. I'm not actually plugging in numbers and evaluating this in my head. I'm not saying, okay, well, let's try cosine of negative 2 pi over 3 and then evaluate it, and then I'm not doing that. I know that because I have something squared, I can automatically just say, hey, I know this is going to be positive. Okay, so I can say that my function is increasing. Now, not quite everywhere. Remember over here, we said it was increasing everywhere because it increased all the way through 0. But remember that it does not, tangent does not exist at negative pi over 2 or positive pi over 2. Okay, so we can't say it increases everywhere. We can say it increases everywhere that it exists. Okay, so f is increasing, or I should say y, I guess. Y is increasing. For all x not equal to pi over 2 plus multiples of pi over 2. And this one, I wanted you to see just kind of what that looked like with a trig function. You're not going to have to write something like in set notation or anything like that. Something like this would not show up on a test or on the AP test, but I just wanted you to see this with a trig function because trig functions have places where we've got asymptotes and such, okay? All right, down here, these are all on that completed notes, so let me know if you have a question on any of those. I'm not going to go over it right now. Okay, this one right here, I'm going to do intervals of concavity. Remember here, we do the same thing that we did for the first derivative to find intervals of increasing and decreasing, but now we want critical points on the derivative. So critical point means the derivative equals 0 or doesn't exist. And so critical points on the derivative means that the derivative of the derivative, or f double prime, equals 0 or does not exist. Okay, so let's find our critical points of f prime by first finding f prime. Okay, and then critical points of this will be where its derivative, so the second derivative, equals 0 or doesn't exist. So 6x minus 6, and then we set this equal to 0. Come over here because I kind of ran out of room. So we get x equals 1 as our critical point. So here's our critical point. So then we're just testing the sign of the second derivative to the left and to the right of 1. Okay, so I'm looking at this. And really you could divide by 6 and say we're just looking at the factor x minus 1, okay, or get rid of it completely. To the left of 1, we've got a negative. To the right of 1, we've got a positive. So f is, let's label our sign chart here. F is concave down on negative infinity to 1, and f is concave up on 1 to infinity. Okay. Before I forget about sign charts, there's a College Board position paper about sign charts, okay, and I'm sure you don't care to read that because that sounds boring to you, but sign charts are definitely a useful tool. That's how we do, intervals of monotonicity and concavity. That's how we do the first derivative test. However, they are not something that is counted for credit. It's considered scratch work. It's not even looked at on an AP test, like on a free response question or anything like that. So while this is how we solve, if you were asked to justify your statement, having a sign chart means absolutely nothing, okay? So if I was asked to justify this statement, if I wanted to prove why f is concave down, I would need to write in words, I would need to say, because f double prime is less than 0, okay? So just saying, oh, well, there was a sign chart there. Why didn't they look at the sign chart? Or why didn't you, Mrs. Easley, look at the sign chart? I'm not going to look at the sign chart there if I'm looking for justification, so make sure you give this statement, okay? And then one other thing with finding critical points. Here, I factored out a 6. Actually, I divided by 6. If the constant that you are factoring out or dividing by is negative, you need to keep the negative with your expression, okay? Even if you need to factor a negative to the front before you can, unfoil, okay, or factor a trinomial, that negative, when we're looking at the sign of a first or second derivative, that negative makes a difference. So what I'm saying is don't divide the whole equation by a negative number, because then all of your signs are going to be flipped on your sign chart, okay? So just be careful with negatives. All right, one more here. We've got another example of the first derivative test. Okay, so we are looking for local extrema. Okay, so we first find the derivative. So that's going to be x squared minus 2x minus 3. And then we set this equal to 0. So then factoring this to solve, x minus 3, x plus 1. So x is equal to 3 and negative 1. So these are our critical points. And then we're going to do test points on the number line of f prime around negative 1 and 3. Please make sure you put the lower number on the left, okay? That'll mess up your number line otherwise. And again, to the left of negative 1, both of these factors are negative. So negative, and then in between negative 1 and positive, this one changes signs. These are actually the same intervals as before. And then, aren't they? Or the 1 and the negative 3 switch. Now I don't even remember. Negative 1 and 3. Oh yeah, they're the same. Okay. All right. So either way, we see that we've got a min at x equals negative 1 because f prime changes from negative to positive. So min at x equals negative 1. And then we have a max at x equals 3 because f prime changes from positive to negative. So max at x equals 3. Okay, and again, if I were asked to justify this statement, I would need more than a sign chart because that doesn't count for anything as far as your justification goes. I would need to say because, like for this part, min at x equals -1 because f prime changes from negative to positive. Okay, max at x equals 3 because f prime changes from positive to negative.